Again, welcome to the last basically session we will have this month, because next time we will meet is going to be Tuesday, November 3rd. So today we're finishing a couple of chapters. Actually, one we covered most of it, namely the musical instruments. We talked about the pitch, we talked about the quality of a pitch, we talked about the interference, the beats, and things like that. So there is these discussions. They are important actually for sound. There is a concept that is there, but it's actually more of a in order to really fully understand it, you really have to get to a little bit of the math, especially trig functions, okay? Short of doing that, and that is Fourier transformation. Actually, it's a little bit more than trig functions. It involves also other kinds of concepts in mathematics. But that's the Fourier transformations, basically. Fourier transformations, basically, in a nutshell, what they are is any periodic behavior, like, for example, waves. Waves, they have periodic behavior in the sense they repeat, okay? Hence the concept of a period. So the period is the time it takes for them to come back again. And the repetition of the waves is actually both in space and time. And like, for example, vibrations, which is just a behavior in time. In other words, the periodic behavior is just in time. However, for a wave, it repeats both in time and space, and you have a period actually in time, which is called the period, and it's measured in seconds. And the period in space is actually called the wavelength, and it's measured actually in meters. So it repeats after every single number of wavelengths or wavelengths, okay? So the same thing. So that's basically what the idea behind it. That's the Fourier transformation. And Fourier transformations will allow us to basically break down any kind of periodic behavior into the so-called harmonic oscillations. And what they are perfect sine wave functions. When I say sine in here, I mean exactly a sine or a cosine. They're identical. They are shifted only with 90 degrees from one another. So that's basically why we call them sine functions, both of them, the sine and the cosine. So those are the harmonics. So Fourier transformation, what it allows me to do is break any kind of behavior into one or more of those, okay? Actually, it's a huge number of them. And the analysis is called the Fourier analysis, and usually that tells you the less basically other components are, the less noise there is, and the purer the signal is, and of course, the better the quality of the signal is. So when you do Fourier analysis, that's what you basically do. So that is from chapter 21, I believe. Yes, chapter 21. I promised you guys to build an instrument for you guys. So this is basically what you guys have here is the deal. If you guys like this very much and you think that I'm doing well with this, so I probably will be, this will be my last semester here teaching physics, and I will probably go on a tour and do musical thing. Is that a deal? Does this sound good? Okay, at least Kyle agrees. Anybody else is awake in here? Okay, Taryn and everyone else. Okay, so we have more people now who woke up. Okay, so here is the trick. I'm gonna build this thing, and I'm hoping that you guys will tell me if this sounds good. So basically, I just pull the straw. So this is a straw of a given length. This is the idea what I'm trying to do now so that you guys understand it. I'm going to send a sound wave from one end, and because the other end is free, this is similar to a string oscillating basically from one end and being free. So it's like a whip, basically. You take string and basically you snap it. So from the other end, it's free. So it's going to form standing waves now, okay? It's going to, depending on how many modes I will excite, I will have a certain nodes and anti-nodes in between. In other words, I will have rarefications and compressions, okay? That's the idea behind it. Now, as the frequency will depend on the length, okay? And you will hear it. You will hear it changing. Because the length is very long, then the frequency in this case should be a very short frequency initially. In other words, the wavelength is long, since lambda is long. And remember, from the expression that we derived, the velocity of the wave, in this case sound, the ones that you're going to hear it, and you know exactly sound, because that's exactly how it's going to be perceived in your ears. So you have an intuitive value, an intuitive notion of what the velocity is, of what the sound sounds, basically how it sounds like. You would say if the wavelength changes, that the frequency has actually changed, because the velocity is lambda times f. If I shorten the string, if I cut it, I mean not the string, if I shorten this tube in here, if I cut it basically, lambda will be less. Okay, so the frequency will go higher and higher. So in order to give you an idea what the difference between a low pitch and a high pitch is, low pitch sounds like somebody basically an older man with a full voice. Okay, that's what low pitch is. A child screaming, that is usually a high pitch. So that's screeching sound, that is actually a high pitch. So what you will notice in here, I'm going to do this in here with you guys live. And if it doesn't work, it doesn't work. That means I'll keep my job, okay? And if it works beautifully, then you guys will tell me that, okay, you're doing well, then maybe you should go and get an agent and start working on this thing. So I'm going to produce a sound from one end, and it's going to travel to the other end, and you're going to hear it, and your brain tells you exactly what the frequency you are hearing. It's going to be a low frequency because this is the longest I have right now. Cut a little bit of it, and you will see a change in the frequency, and that change toward the higher frequency, okay, higher and higher pitch, until I get to the point where it's super short. At that point, you will see a high frequency, the highest that I'm going to do in here. Usually, if you're doing this, you would want to make a little bit of an end in here to help you basically with sound. Okay. Okay. I think that's good enough. If it doesn't work, we can work on it. Who thinks it's going to work? Who thinks it's going to fail? Because that's usually what happens, okay? Come on, guys. You need to wake up. Okay. Okay. Oh, it did not work. Excuse me, guys. What happened in here? Did you guys notice? Okay, it's laughing. Did you notice the change in frequency though? Yes or no? Okay, so it's succeeding, I guess. So I'm good. Did it pass? What do you guys think of this number? Okay. When I do this live, and I always do it, right now I'm having a little bit of headache because blowing on this thing is not easy, okay? When I do this in live, thank you everybody. Okay, thank you for the encouragement. When I do this live, I notice that my students start to tear up, basically. They will have tears in their eyes. I don't know if they're really loving it to the point where they have tears or they're laughing at it, so I don't know, okay? So that's the point of it. Now, here is the deal. What I did actually in here, let's go serious a little bit. It was long, so the frequency you guys noted was very high, very low, sounding like woo, okay? Until I got it to this short, okay? And that is a super high frequency compared to the one I started with. So that's how it's sounding right now, okay? So what happened if I cut this by half? It's going to be even higher frequency. Okay, what happened to this scissor? Okay, for the two of you who just came in, you missed on a lot of fun. Okay, so I promised you guys, and you're gonna tell me, at least somebody has encouraged me to basically go on a tour and be a star. I don't know about the rest of you, but it seems like I may be going, okay? So next semester, probably I will not be doing Physics 10. Anybody else thinking that they should quit other than Kyle? Did I do this number for nothing? Turn, I used straws. The straw, yeah. Okay. Okay. So hopefully you guys have had some fun with this too, okay? Because I usually do. Anyway, the point being in here, it's standing waves. What you have witnessed actually is this relationship. Let me write it down for you. You have witnessed V equals to lambda times frequency, okay? As I was changing the length, making it less and less and less, in this case, lambda was getting less and less and less because V is the same. For you, your ears have an understanding of what the velocity of sound is. It's 340 meters per second, numerically speaking, okay? So that did not change for you. So you know the speed of sound. So what happened to when lambda becomes less, F becomes higher, the frequency becomes higher and higher. So that's why the pitch was changing from a very high pitch, from very low pitch, I'm sorry, where F is very small, to a higher and higher values to the point where we got it super high frequencies, okay? So that is my understanding of music, and that is my version of it. So I don't know if anybody else enjoys it, but I enjoy it a lot, okay? So I guess probably other people might not like it so much. So we're done with chapter 21. Let me go back into the notes and see exactly the main points from that chapter. Stuff that we discussed so far. Everything we discussed in this chapter, we discussed it actually in the sound, okay? The concept of noise. The noise is the fact that you have too many frequencies and they cancel each other, all kinds of frequencies, and you have a lot of cancellations and a lot of basically things that add up to no harmony. When you have standing waves in general on a string, for example, that is when you perform, when you do the when you have exactly specific frequencies that are going to emerge. Okay, I have a string in here, and this is of course it doesn't sound probably as pleasant as what other musicians do, and that's why they get paid the big bucks. But that is basically what you form in this case. I'm holding it from both ends, so I'm trying to form standing waves on this. Okay, and as the length changes, the tension actually also depends on it. So that's why because the velocity of the wave on a string depends also on the tension. And that was one of the questions we discussed a long time ago in chapter 20. Okay, when we were talking about the sound. Okay. Again. The pitch, the sound, the intensity, again, how loud it is, it has to do with the amplitude, okay? And you have amplifiers in the case of music to amplify sound. And the quality, again, depends on the idea that how many tones there are in a single note. So basically, that is, the less they are, the higher the quality is, okay? I'm not really an expert in musical instruments. The only instrument I'm expert in is the standing waves on strings and also on straws. So that's the question of Taryn. So that answers her question. I don't know any other instruments. And Fourier analysis, I talked about that, and the DVDs, that's another idea in there that has to do with how sound is recorded and things like that. Okay. So let's move to the next topic, the next big topic that is going to have tremendous applications in terms of the next exam, which is the final, okay? And that is electricity or electrostatics, okay? So That's something that people has experimented with this one from the dawn of time. People have wondered about lightning, for example, and they associated magic with it. And you have those, whatever, those people who took advantage of it. They're the magicians and things like that, and they can summon the power of the lightning and things of this nature. But of course, they did not really understand it fully. It was until later people started to really experimenting with it until they have an understanding of it. So let's talk about it. What I have in here, I have a balloon, okay? I had actually another one, but I couldn't find. I had a actually very nice rod that actually builds statics, electricity, but I don't have that. Here is the trick. I have a piece of paper in here, okay, that is attracted to the Earth due to the gravity. So this is the entire planet, you and I combined, the Himalayas mountains, and what else also is on the Earth other than you and I in the Himalayas. Everybody else, okay, including Donald Trump and also Mr. Biden together, we're all pulling on this toward the Earth, okay, combined, all of our forces, basically, all of our masses pulling on this tiny thing, okay? And here is a balloon, okay? I'm going to rub it against my shirt in here, jacket, actually, okay? This should basically interact with this jacket enough to basically create charges. And those charges, by pointing here, are going to overcome the power of the entire planet. And you and I combined, the Himalayas, Biden and Trump, were all pulling from here. Yet this balloon was able to pull it towards it. So this is a very, very powerful force, okay? Much stronger than the force of gravity, because this balloon, which is actually a lot lighter, actually I'm holding it myself with my hand, and combines by itself to overcome me, you, the entire Himalayas mountains, everything else on Earth, including Biden and Trump, and yet it overpowers us. So this is the electrostatic force, okay? And all of you have experimented with it. This force is so important that it powers everything else nowadays in technology. The only reason why we're holding this session is because we have a better understanding of electricity and magnetism, okay? That's the other force in here too, the force of the magnets. You have two magnets also. They're going to interact so that they overcome the same force of gravity. So this magnet is being pulled toward this magnet, and actually it doesn't have to be a magnet. It can be a piece of iron in here. So this is normally would fall. This is a paper clip. Again, the force in this case is pulling on the paper clip in here, as you can clearly see. So the point being in here is these forces are so powerful, okay? Probably I should not have done this thing while we have that. So let me go to a better view so that you will have a much better image of this. So again, this you have experimented with it, and you know it, I'm sure. This is everybody's toy, especially when you're young. So you experimented with this one. Who did not play with balloons, okay? That's also another thing. It's still really holding to it. So the charge in here is still holding to it. As a matter of fact, this is so powerful that it's still in place, okay? So let me try to free it up. It's trying to escape from my hand, okay? Now it's gone. The same force, actually, and I have a very nice activity for you guys. Probably we can do it later on. It's for the involving tapes, actually, that you can demonstrate the charges and things like that using a regular tape, you know, like Scotch tape. So there's all kinds of things, interesting things. So this stuff is very important in terms of nowadays technologies, because it helps us. It helped us a lot. So we're really living the revolution of this electricity and magnetism. Without it, we would not have all of this electronics. Basically, we're communicating via it. You guys are very far away from where I am at, yet you're hearing me, you're watching me. The same thing with phones, TVs, everything else is based on what happened in electricity and magnetism, and a further advancement in the science of electronics, which is actually a little bit more refined stuff in it. So this is basically a big introduction to this topic. So let's continue with this, which we're going to be covering in the case of electrostatic. Of course, we're not going to hit it from the get-go all the way through. we're going to introduce it little by little. So the electrical forces and charges, we're going to talk about the force itself, and the conservation of charge. This is one of the most fundamental laws of nature. Okay, I had a class actually when we were face to face in the past. I don't remember exactly when, and I asked about the laws of conservation, what is conserved in nature. This is one of them. Whatever the universe had in terms of charges to begin with, that is the same amount. It never changes. If a positive charge gets created, a negative one also gets created in the same time. So whatever you started with, you end up with. If one of them is destroyed, a positive charge somehow goes away, it has to go away with its counterpart. So the positive go away, it must have consumed with it also a negative charge. So this is a basic law of nature. This goes exactly the same thing with the law of conservation of energy, for example. Okay, this is actually far more rudimentary than that, far more elementary than that. And it's really it plays also a major role when we do electricity, when we're trying to understand what happened to currents. Imagine with me a wire. This wire. Okay, and for example, another wire connected the two wires in here, end to end. Okay, so the charge that's, for example, if I happen to have a charge flowing in here, moving around, when it reaches this junction, it must continue in here. So if I have 10 charges going in here, they must come from the other side. Now, what happens if I take this other wire now and connect in the same junction? Now I have three wires in the same junction. I'm holding them in here to show you that there are actually connections. These wires are all connected in here, okay? So if 10 charges, for example, come from this side, when they reach this junction, and let's say, for example, I counted 3 of them going through the red one, how many do you think went through the black one? I started with 10, and I counted 3 here. So how many do you think go into the black wire? 7. Does everybody agree with Kyle? Yeah, that is the conservation of charge. Because if you started with 10, you must end up with 10. You cannot have more or less than 10. So if this 3, I found them to be here, then 7 must be here. If you understand this idea, you understand half of electricity, have half of how circuits work. Okay, that is where current split. That is how currents actually split. When you have a splitter, when you are splitting actually currents, not voltages. Okay, the other idea is the voltages, and that has to do with the energy. Okay, which is conserved too. So that is basically the essence of how electrical circuits work. So then we're going to talk about Coulomb's law. Coulomb's law is really the one that gives me how strong this force is. Okay. Then we're going to talk about 2 kinds of materials. There are materials that conduct electricity, like this wire. This is a conductor, the one that you see in here. This is actually the same wire, except that it's stripped from anything. Okay, that's a conductor. This one too is a conductor, actually. And this one is not. This material is not conducting material, doesn't conduct anything, actually. Plastic is not. This rubber doesn't conduct actually electricity. I mean, it holds charge, but it doesn't conduct at all. Okay, that's why we use plastic in here to insulate the conductors. So those are insulators. The plastic itself, not the wire inside of it. The wire inside of it is actually a conductor. So that is the 2 main types of materials. There is a 3rd type that is not listed in here, and they are the semiconductors. Semiconductors, where is my diode? They play a major role in nowadays electronics. Without them, we would not have none of this electronics, basically transistors and diodes. And I'm looking for my diode in here, and I don't have it. Okay. Yeah, do I have a transistor? Yep, I do. This is actually an entire circuit in here. So what you see in here, this is actually an entire integrated circuit. This one also is an integrated circuit, and they are all relying on semiconductors, actually, not on conductors or insulators. They are all relying. Did any one of you play with this Uno thing, Arduinos? Anyone is familiar with the Arduino boards? They're a ton of fun. So it's a good idea to get going if you never did it. Go and buy a kit and start playing with it. They have several kits of this. Okay. So that is one thing in here. So that's semiconductors. Semiconductors is really the essence of everything that we have right now is semiconductors. Actually, we have conductors. For example, this circuit will not work without this this conductor. I have here a what is it? A breadboard in here to help connect other stuff with it. But you need wires, of course, at the end. Otherwise, this thing will not work for you. Okay. So this is the. So you need conductors and you need insulators too. Both of them, I have them in here in this. This is actually an insulated conductor. Conductor inside in here. So that is actually the conductor, you're looking at it. And it's insulated. So those are the two types we're going to be talking about in this class in here. In addition to that, we're going to talk about a third type of material, superconductors. I don't have any superconductors in here because I really need to have super cold temperatures for us. And this is used usually in laboratories nowadays, or actually in a highly advanced technology to produce, mainly at least in laboratories, to produce a lot of other things, among other things, to produce extremely high magnetic fields. Okay, so they're basically conducting electricity. They're conductors, but with no resistance, which is kind of a nice thing to have. Okay, and then we're going to talk about the charging, how to charge things, and then polarization. This actually, the process with which this took the paper was through a process called an induced charge. Okay. Polarization has something else to do with the electric field. So we're going to talk about that electric field and the electrical potential and the electrical energy. Electrical energy is how much, for example, is energy stored in this battery in here. Okay. Depends on how many hours you can get out of it. I know it's 1.5 volt, and 1.5 volt, depending on how much current you're going to get through it through the entire period of time that is exposed, that is the energy that is stored in there. Okay. The power company will always charge you only for the energy you consume. The fact that the power company delivered the 120 volt to your household does not mean that they are going to charge you for that. They charge you only when you plug a device to that 120 volt and start draining charges off of it. Okay, that is the only time when they start billing you. That's when they make you pay for it. So again, electricity, as I mentioned before, was something that was experienced by early people from the early dawn of time through ideas, for example, lightning, sparks. So things like of this nature. So when you hit those two rocks, you produce actually a spark in there. And the electrostatic involves, of course, charges. You have to have a charge to play the game of the electrostatic. For example, here is the deal. We're going to measure the force of the electrostatic, and we'll find tremendous, like I showed you an example, for example, of the balloon holding a piece of paper. That piece of paper is being dragged by the entire planet, yet this balloon, tiny balloon, was able to overcome the entire Earth with everybody on it. Okay? Meaning that this electrostatic force is tremendous and it's super strong. Okay? As a matter of fact, compared to gravity, if they have a proton and an electron, they should fall on each other. Or if they have a proton and a proton, they should repel each other with tremendous force compared to gravity. Compared to the force of gravity. Force of gravity, you try to bring the two protons together. But this force is 1, followed by 40 zeros after the 1. 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 40 zeros. I don't even know how to say the number. Nobody actually knows. There is no name for it. I mean, I know a million is 1 followed by 6 zeros. I know a billion is 1 followed by 9 zeros. A trillion is 1 followed by 12 zeros. I don't know what comes after that and after that, and it's not enough. Imagine a trillion of a trillion, which is 10 to the power, what, 24? And you have to add another trillion and another trillion of a trillion of a trillion of a trillion to get that number. That's how powerful this force is. Super powerful, very strong, okay? So this is the electrostatic force. Here is the problem. If it is that strong, and let's say, for example, tiny portion, 1/1000th, if you wish, okay, of our atoms, for example, goes and get ionized, loses a charge. 1/10000000. It's nothing. I mean, out of 1 billion atoms in your body, only one of them. The rest are neutral. We would not be able to sit still. We will fly apart. We will break apart. The entire planet will break apart because of this force, how strong it is compared to the force of gravity. Yet, the force of gravity wins. The force of gravity is the one that holds us to the planet, that holds the entire planet together, that holds the entire planet to the sun. The entire solar system is actually glued together, not because of this force, but it's because of the force of gravity. The entire universe, actually, in the galaxy is held together by this gravity. So, albeit it's very, very tiny, the one that we discovered so far, this force is so powerful. The only reason why it does not dominate our daily experiences is because everything comes in neutralized. So for every positive charge, it has its own counterpart, and basically this force does not play any role. Unless, of course, you have charges isolated and you see flying sparks, and that's a tiny charge actually, okay? So the lightning that you see there is due to some charges, and that is because the imbalance was somehow broken, okay? The balance was somehow broken. So this is basically, in a nutshell, how powerful this force is. So again, take this balloon, for example, after I rubbed it through my jacket, okay? Now I know it has a charge, okay? It has a charge. I can take this charge, for example, and create another balloon and split that charge 2 ways. What is wrong with this thing? It's not blowing. Oh, it's torn. Sorry, there's a hole in it. Okay, anyway, my point in here, I can actually connect the two balloons, and now all of a sudden, I have the charge that is divided by 2, okay? And I noticed that similar charges will repel, okay? Whether positive and positive will repel or negative and negative will repel. But unlike charges, positive and negative, they always will attract. That is something that we learned way back, okay? So in the case of the atom, this is no secret. Some of you probably took some chemistry. You know that there are 3 kinds of main particles in the atom. There are the electrons that sit more or less outside of the nucleus. I mean, sit outside, well outside of the nucleus, and they have a negative charge. Okay, the way that we chose them to be negative was actually by convention, a weird convention, but at the end they turn out to be a negative charge. If tomorrow, for example, we meet another civilization, they might end up having charges that are actually where the electrons are positive. If that's the case, then their protons will be negative. And if they do that, they will have a much better luck at understanding better electricity than we do, because nowadays, if you connect this battery, for example, to a resistor or something, the electrons start flying off from this side going to here, but the current on my needle will show the opposite way because we chose the wrong side for the electron, okay? But that's a convention. So the fact that one of them is positive and the other one was negative was just a convention, okay? Now, inside of course, in here, you have a problem. The electron and the electron, they have both of them negative charges. Of course, they don't want to stay next to one another in terms of electricity. Same thing in here, the proton and the proton, they don't want to be next to one another. The neutrons, in terms of electrostatics. So you're wondering what's going on in here inside the nucleus. How come a proton? This is the atom of helium. So how come in this case I have a proton next to a proton? Well, in this case, there is an even stronger force that will glue these things together. And that force is actually the nuclear force. Okay. So the nuclear force does not do well at far distances, but the minute the proton, so they're repelling one another. Think of them, they don't want to be next to one another because I just explained from the previous slide that a positive and a positive would repel one another until at a certain distance, actually, they will pull to one another due to another force, that is attractive force, actually, always in this case, between the proton and proton, and that is the nuclear force. So when it comes to nuclear forces, the proton and the proton, they're going to stick to one another. Here, the neutron is not participant in this game of electricity, okay? In order to play this game, you have to have a charge, okay? In order to play the game of gravity, you have to have a mass. All of them have mass. So all of them are allowed to play the game of gravity, protons, neutrons, and electrons. For the game of electricity, neutrons, they're not allowed in. They cannot play the game of electricity. The only players in here who are allowed in this game are electrons and protons. As a matter of fact, on our daily experience, the electrons are the ones who actually dominate the game completely. The reason being is because they're lighter in terms of mass, so they're much easier to move around, okay? The only reason why you're seeing me right now is because of the electrons inside your retina. My camera is taking pictures, transferring it through the internet, coming to you. Your computer now is taking it from there and making an image. The electrons in your eye are actually the ones who are moving back and forth, and that is interpreted as a signal in your brain. Same thing, the only reason why you hear me is because of the electrons. As a matter of fact, the only reason why you're seated somewhere is because of the electrons. Your electrons from your body and the electrons from where you're sitting on, they interact with one another and they repel one another. The only reason why my hand is not going through my other hand is because of the electrons. So in our daily experience, actually, electrons are the ones who play the main role in terms of this, and they're actually electrostatic forces, okay? So this is in terms of how the atoms are working. Now, two things. Because of the conservation of charge, the number of electrons and the number of protons is the same. That's number one. And they also have the same charge. Electrons and protons, they have the same charge. So that is item one for the discussion today. So comparing electrons and protons, the number of electrons and protons is identical. Not only that, but also they have the same charge, numerically speaking. So if you cut it in any other way, you cannot do it. I mean, if they were a little bit of an imbalance, things would have been weird in this universe. Okay, so that's the item one. So we have the same number and the same charge for electrons and protons. Yes? Everybody on board? Good? Yeah, we have to. Okay, here's Josh is with me, Amanda, one of the Amandas. Okay, Jeffrey. Okay, so let's continue. So every atom is composed of positively charged nucleus surrounded by negatively charged electrons. Each of the electrons in any atom has the same quantity of negative charge and the same mass. Now, the thing to say about the previous statement that I said for the discussion is a neutral atom, okay? But the thing with it is that overall in the universe, they must be the same number. Okay? That is because of the previous statement about the conservation of charge. Another fact about these things is that the atom protons are about 1,800 times more massive than the electrons, okay? Hence, they have very high inertia, relatively speaking, and they don't get involved in terms of electricity. That is really the reason why they don't get involved. Neutrons, they don't play this game. It doesn't matter how light or heavy they are, okay? They're period, they're out of it. Okay? When they say usually in here, they mean when they're neutralized, unless an ion is. An ion is a positive ion is when we have a net loss of electrons, and a negative ion when we have a net gain of electrons. Did any one of you take a little bit of chemistry or in high school or somewhere else? Or physics that covers these topics? Okay. At least some people did. So you know these things. If not, this is part of the things. Yeah, this is part of the things that you guys should know anyway. So the innermost electrons also, they are not really allowed to play the game of the because they're anchored into the nucleus. The ones that are outside are the ones who can actually move in, or you can add to them stuff. Okay, so depending on where they sit on the periodic table, some of the electrons, they are much easily basically they can be removed from the. Usually these are metals. Okay. And some of the other basically elements on the periodic table, they can actually easily gain electrons, like the ones who are sitting on the other side of the periodic table. Okay. Okay, we did this actually. We didn't do the comb, and I don't have much hair to do it anyway, so sorry. Okay. And I had the glass rod. That's the one I was looking for, and I was actually readying it for you guys. Sorry, I did the balloon. That's good enough? If not, do that on your own. It has to be an insulating material. You cannot try it with a conducting material, because if I try it with a conducting material, I'm not going to succeed. And the reason why I will not succeed is because of the fact this is the conducting material. Let me tell you why. Because conductor will lose its electrons quickly, so it's not going to do well. Okay. Conductor is not good. I mean, the trick with the insulator, it doesn't conduct electricity. The only reason why is because it holds it. It holds it in place. Whereas a conductor doesn't hold charge, so charge comes through it from one end to the other end, and that's why that's the big reason why. When you brush your hair and scrape electrons from your hair, the charge of your hair now, you remove the electrons, so it has to be positive. Okay. It would have been great fun if we're sitting in class and we do the Van de Graaff machine. For some of you who have long hairs, you will see the hair going all over the place with the Van de Graaff machine. Did anyone experience this in the science center or in a science class? Do you guys do the Van de Graaff, where you have your hair sticking out? No, Kyle did not. Whose hair is like mine, not much or none at all? They will not experience that. You don't have to answer this, okay? I'm sorry. Okay? So if you're lucky like me with no hair, so you're not going to experience that. But if you're not lucky like me and you have a bunch of hair, then you're going to have hair flying all over the place, okay? If you do the Van de Graaff. And we used to do science nights, and I used to have that thing there. You used to have magnets. You used to have another thing also with Faraday's law, and it's a lot of fun. Okay, when you have people standing in there and holding the Van de Graaff, and you're building charges, you're building voltages actually, and the voltage can reach sometimes several thousand volts. And you have to make sure the person is standing on actually an insulating material, otherwise they will be electrocuted. Not that much, they will just, they feel a pinch, okay? Anyway, so that builds charge actually, and the charge in the body will go, actually they're going to be electrons, and your hair is going to go all over the place, and you feel it in your skin and everywhere. So again, We talked about this point in here. So if you have negative charges basically taken from the rod, then you must have left with positive charges, because again, charges are conserved. Okay, that is the second point I'd like you also to have and to mention today in the discussion: the fact that the conservation of charge is a fundamental law of nature. Yes, so we have two topics so far. Conservation of charge is fundamental law of nature. I know it's related to the first question, but this is by far a big deal. Mr. Coulomb, actually, what he did was he summarized the work of a lot of people before him, and he found this force, the force between two charges. And he stated that this force actually is proportional to the charges, okay, charge 1 and charge 2, and is inversely proportional to the square of the distance between them. The further they are, the less they act on one another. The closer they are, the stronger the force. Just like the law of gravity, except the law of gravity had the product of the masses divided by the distance squared, then had a different constant, okay? So that's the only difference between it. And this is basically the law that he arrived to. Now, this constant, kappa, which is the, actually it has to do with permittivity of the medium, it has to do where you are, is 9 times 10 to the power 9 billion in the SI units. Versus when we did gravity, gravity was, it had the G in here, and G was 6.67 times 10 to the negative 11. So that was 0.0000, basically 11 or 10 zeros and then a 6. So, and this constant now is 9 followed by. So this constant actually gave us an idea of how these two forces are imbalanced. Okay. So the two forces we discovered up to now in this class are the force of gravity, which is super weak because of that G in it, number one. And the kappa in here, the constant of the in this case, which is the it has to do with the permittivity of the medium, is super strong. Okay, super strong, much larger than the other one. 9 billion versus 100th of a billionth. Okay, 100th of a billionth, which is 0.00000006. Okay, so the charge in this case has the units of Coulomb. Obviously, this is the law of Coulomb, and he did not name it after himself. All he did actually, he did a lot of work actually in the area too, but he summarized a lot of other people's work, where they take similar charges, they put them at this distance, they move them away, they measure the forces, they move them away, they measure the forces. Usually they only move one, they don't move the other one. The other one is anchored actually, and the second one they move is attached to a spring, and they measure the force as this one moves further and further and further. And that's how they saw the effect of 1 over distance squared. Now, you take two charges and basically take this one and connect it with this one. So now you have similar charges. Take this one now connected to completely uncharged the charge. Now this one drops by a factor of 2 again. And now you bring the third one back to the initial one, and you see how is the strength of the charge now changes. So they did a lot of work in that time, and it took a lot of time to get to this law. But that's how the law works, okay? Both of them, interestingly enough, are dependent on 1 over distance squared. And this is something that is kind of spectacular in this case. Both of them have this 1 over distance squared. Even the nuclear force, the one I mentioned earlier, between the proton, and actually the neutron and the neutron and the proton and the neutron inside the nucleus, that force also has a 1 over distance squared in it. And it has actually a factor on top of it, an exponential of some distance, to kill it for larger distances. That too depends on 1 over distance squared, which makes you wonder what is deal with the 1 over distance squared. Okay, some people speculate that's the secret of living in the 3-dimensional universe, and probably it is. So again, if you multiply the distance by 2, or you half it, if you half it, you're going to have a quarter as strong. So basically, here's the deal. No, if you double it, it's going to be a quarter. So let me stop sharing the screen here and share with you this screen and open Physics 10 tab. Get my pen. So basically, I know the force, initial force, is some constant times the two charges divided by some distance squared. Okay. Now, if this distance now is doubled, so instead of distance d, I have two distance squared. The whole thing, of course, I double just the distance. So I have to square it by this number. I still have to multiply by Q1 and Q2 and multiply by K. So this expression now, when I square 2D squared, is actually 4D squared. So it's going to still be Q1, Q2 divided by 4 now times D squared times K. So this is the old force that I had in here. But instead, now I'm dividing it by the factor of 4. So for example, if the force was 10 Newton, this is going to be 10 Newton divided by 4, which is 2.5 newtons. Okay, so this is basically what that means. So if you double the distance between them, the force now drops by a factor of 2, by a factor of 4. So if this is, for example, one charge, and this is a second charge, and I measured the force with this spring, for example, and found this force to be 10 Newton. Now, if I double the distance between them, mainly put this one, not here, put it at twice the distance here. So this is now, I have doubled the distance. And I bring the reading on the spring, I will see the reading of the spring is actually dropped to 2.5 newtons. Okay. Obviously, if I bring them closer, if instead I bring them here, okay, half the distance, then the reading should be 4 times as much. It's going to be stronger force. Okay. So this is basically how, in a nutshell, this works. So it's square law. Now, if I move them a third to the 3 times as far, so if I move them, so this is still anchored in place, okay? So if I move them 1 unit, 2 units, and now 3 times as much, this force will be hardly 1 Newton, 1.1 Newton. Basically what it is going to be 10 over 9 because the distance has tripled. So in this case, the force has to be 3 squared, which is 9, and this is roughly 1.1 Newton. Now, if I actually bring it to a third of the distance, so this is the initial distance, this is how far it is, this is where this mass is. Now, this is 1/2, this is basically where 1/3 is. So now it's going to actually be 90 newtons, because 9 times 10 is 90 newtons. So it's stronger when they are closer, and it's very, very weak when they are far away. So that is the effects of the distance on the electrostatic force. Oh man, time is running, so we're running out, so we really need to get going. We are a little over midway. So differences between, again, I mentioned this several times, that this is several times higher, okay? So this one, first of all, can be positive, can be attractive or repulsive, okay? So 2 charges of the same charge, they can repel one another. 2 charges of different charges, they can attract one another. The force of gravity is always attractive, okay? I mean, everything is on the ground because of the force of gravity is always attractive. The only reason why that is because we don't have negative masses. If we have negative masses will be falling to the screen, to the roof, okay? So that's basically what happens. So if you have a negative charge in here, that negative charge actually will fall to the ceiling. And so look at your ceiling. If you see something stuck in there, not due to paint or due to anything else, just due to gravity, that has a negative mass. Nobody has discovered the negative mass at this point. So that's one difference, okay? It can be either attractive or repulsive, whereas this one is always, that we have noticed so far, it's always attractive. So maybe there was negative masses, but those negative masses, because of the fact that they're negative, ended up on the other side of the universe because of the force of gravity, okay? I tried to do this experiment earlier, but I was not succeeding. The only reason why, this is an induced actually charge, okay? I think the only reason why, I'm trying to do it on the one here, is because I think I don't have a good enough, it's stuck more or less, okay? It's coming slowly. So what happened in this situation in here, initially it did not work at all for me. Now you're lucky, guys. It's better than what I did. So what happened in this case, I have induced a charge. So when the balloon was near the wall, actually I did it in class one time and it stayed the entire period there, okay? And at the end of the period, actually starts to fall down. So what happened in this case, it induces the charges, depending on the humidity actually too. That's really a problem too. It's going to attract charges towards it, induces positive, and moves the other charges to the other side. So this is basically how the polarization works in here. It polarizes basically the wall in this case. Again, I mentioned the fact that we have good conductors like aluminum, like iron, but more in the industry, what we use copper. Okay. For those sitting in physics 11, we're going to build a motor, and you really have to have it out of copper. As a matter of fact, if you're trying to buy it, it's going to come out immediately out of copper. So that's what is used actually in the industry. That is the metal that is used. Okay. And but anything else actually is a good conductor. Actually, silver is a better conductor, but you don't want your house to be run with silver. Gold is even a better conductor, but gold, you're not going to run your wiring in gold, I mean, unless you don't care about money. Okay. So that is conductors. So all metals are usually typically good conductors. Some compounds also are conductors. Rubber and glass and wood and things like that. They don't. Air actually is a very, very good insulator. Okay. So you have insulators and you have conductors. If air is not a good conductor, will have electricity flying from the plug all the way to where you are. Okay. There is a breakage point for every single insulator though, and that's why you see lightning. When the voltage becomes so high, there is lightning. Okay. It is semiconductors, those I mentioned already. Okay. They're based on silicon and germanium from the periodic table. And then you have, and they are used extensively in modern electronics. The conductor, so that we have an understanding what it is they have available electrons. They don't belong to a specific atom. They belong to the community of atoms, and they are readily movable. So right now, I can shorten, that's not a good idea to do. I don't want to do this on a 9-volt battery. I spend a lot of money on that. I want to. Even this one, I need it for my experiments. You can shorten it, basically, and you will make the conductor, basically, in this case, because it has available charges, they're going to move from one end to the other end easily with a voltage difference. Now, the battery's role is always to push them in the wrong place. That's really what the battery is. But when they are on the conductor side, they will move in the proper place from the high voltage to the low voltage. Okay. So that's the conductor. The insulator, on the other hand, the electrons, they're anchored to their atoms. They don't want to move. That's why when you put them, you will find them. So even if you put a battery across it, it will not move the charges because it doesn't have charges available freely to move. So that is the main difference between them. Semiconductors, they conduct in one direction, but they don't do it in the other ones, yielding themselves to logical circuits in a sense that you will have current moving one way and not the other, and then you can have a plus, you have a 1 and a 0, and that is why they're used extensively in electronics. Okay, superconductors they use actually in other applications, and those applications involve, for example, high magnetic fields or magnetic levitations that involve actually magnetic fields too, and things like that. Okay, here is something in here. When you go, and I went actually to the store the other day to Home Depot, trying to find the high gauge wire. When you buy a wire from the store, it comes with its electrons already. So the electrons are part of what you buy. And like, for example, if I wanted to buy pipes in there for the conduit for water, for example, it doesn't come with water. That is a point in here. So the charges that move in your circuit, actually, they are already there. The battery, what it does is it pushes them from one end to the other. And when they land to the other end, it's going to move them in the opposite direction and force them to move basically all the time. So that is the role of the battery. It's not to provide you charges. The power company does not give you charges. What it gives you a difference of potential of 120 volts, the purpose of which, if your wire end up with the charges basically in the wrong direction of the battery, is going to move them. If they end up with the wrong node of the power plug, they're going to move them in the opposite direction, and that's it. So that's all they do. And like the water company that actually sells you water. Okay? And when they run out of water, they run out of water, period. This one, they don't sell you electrons, they sell you just the difference between them, they maintain it. So if they tell you, we're gonna guarantee you 120 volts, they were going to guarantee you 120 volts. And your electrons are the ones that are going to move around between those 120 volts, okay? It's like the water, basically. If the water company is going to do the same thing, it's going to guarantee you that you're going to have 12 meters, for example, of height between your waters. But it doesn't do that. It doesn't guarantee you 12 meters, guarantee you actually the water. So that's one thing that is different between the two. So they are already in the wire. Superconductors, these materials have zero resistance and infinite conductivity, so they have tremendous applications because of that. I wish, and they're usually at low temperature, okay? Because they don't have resistance, they don't experience losses due to heat. So they're perfect material for a lot of applications. Okay, again, we saw how we charge the, actually I did it before you guys on how to charge the electrons, basically strip them from one place to the other. In the case of a storm, there is actually buildup of the charges in the, because of the rubbing actually of the different storm components, and that builds up static charge in it, okay? And you will see lightning when the voltage reaches a certain number, okay? It becomes so high. Of course, the tallest building now will be struck first, or the tallest thing will be struck first. Again, this is the idea of charging. So you can charge by contact in this case. You can induce a charge in one of them. And once the charge is induced in one of them, the other one has actually the opposite charge. When you move them away now, all of a sudden you have now created charges. So by induction also. Some materials that are polarized by nature, like for example, the water molecule. Okay, it has actually the electrons of the hydrogen do not, the two hydrogen atoms do not go completely near, they don't go completely to the oxygen, but rather they stay closer to the oxygen, creating a positive and negative side basically to it, okay? Again, when we demoed this with the wall, that is actually created also polarization in this case for the wall. And that's how you had temporarily a connection in here. So again, this is the example that I'm talking about in terms of the wall. And the same thing with the paper earlier when I did the experiment with the paper. The way that the paper basically was attracted to the balloon is by inducing a polarization. The paper is neutral. It has no charge whatsoever in it. What has charge now in it is this guy, okay? And I said that in order to play this game, you have to have a charge. Now, the paper has no charge. I did not do anything. I didn't mess with the paper at all. What I did was build a charge in this thing. No, it's not. Yeah. And now all of a sudden it's attracting to it. And how is it? It's because it has built up charges of the opposite side on one side and moved the other to the other side. That's it. So it has induced charges in it. In order to play this game, you have to have a charge. The paper does not really have a charge. So what the balloon did in this case is induce charges in it. Move charges. Okay, so that's exactly how this is working. Same thing with the case of the wall. This is a hydrogen atom. I already mentioned the fact that it's polarized, okay, and it's like an electrical dipole. We'll talk more about the electrical dipoles down the road. The electric field is a measurement of the strength of how much a charge can, if you wish, pull on other charges, okay? I don't like this word aura in this case. Basically what it is you have a charge, you bring a test charge or 1 Coulomb charge next to it and see how much force is produced. That is what the electric field is, okay? And if the charge is negative, the electric field is going to be pointing towards it because the 1 Coulomb actually will be attracted to the negative charge. On the other hand, if I bring a positive charge, the 1 Coulomb will be repelled from it. When I say 1 Coulomb, I mean exactly a positive 1 Coulomb. That is the test charge on how to test the electric field. The units then for the electric field are Newton per Coulomb, because that 1 Coulomb is the value that I have. Now, if I don't bring 1 Coulomb, or we're fresh out of 1 Coulomb, if I go to the store and ask for 1 Coulomb, and they tell me we don't have one, so I can bring any other charge I want to, micro Coulomb or a milli Coulomb, any small charge, but instead, I'm not going to read the force actually on 1 coulomb, so all I have to do now is divide by that number. So the electric field and the force are related in terms of one another in terms of this expression. Okay, so the electric field is somewhat a measurement of the force, except it's not really a measurement of the force. So it's a force per unit charge. So this is how the expression is read. Where is my pen? Did any one of you see my pen? Oh, here it is. Sorry. Okay. So this force I was talking all about now is this, now expressed in terms of, mathematically of course, Q times E. So this is the charge. So this is what we call the electric field. And this is the force. The force that I measure with this device, spring, okay? So that force is the one that I'm going to measure. So this is basically, then the electric field can be measured in the units of force, which is Newton, and the units of charge, which we already mentioned, is Coulomb. So that's basically how this expression is. Still have a couple of points and then we're done. So remember this, the electric field always points towards the negative charge and away from the positive charge, okay? It's like, and this picture is kind of a little bit misleading because this is a 3D picture. So it's like a hedgehog everywhere. It's going, not just on a plane. It's going every single direction, okay? So whichever way you look at it, it's coming to you. Because this is how the electric field would look like. So it's not a arrows out of, it's not like a, and how strong, how many arrows we will have come out of that, depending on how many coulombs you have in there. So that is basically how the electric field is. Again, this is what I was talking about in terms of the Van de Graaff machine. So basically what we're doing in this case, we're building charges, and that's how the hair starts to fly in here. Okay, again, similar to the fact that I have, because when I put charges in here, a positive charge and a negative charge, and hold it in place, I have energy. If I let go of it, that particle is going to move and it's going to do work. So it has a potential energy, actually, just like the force of gravity in this situation, and like the force of spring. If I have positive charge and negative charge and hold it in place, I have energy. If I let go of it, it's going to fly away and can do work for me. So there is an energy associated with the electrostatic force in this case. So the electrical potential, the potential basically that we talk about, is related also to the electrostatic potential energy in the same fashion as the electric field is. So let me go back into that slide to illustrate this point in here. So the energy, which is usually has a symbol U, and so this is the energy. This is in joules. This is the energy that you know and love. Is also equal to the charge times the voltage. So this is the voltage, and this is in volts, actually, the units for it. And this is the charge, the same thing, in Coulomb. So when I have 1.5 volt in here, or when I have 9 volt in here, I have a potential, electrical potential. If I drain 1 Coulomb in here, I have actually taken 9 joules of energy. If I drain 1 Coulomb from here or move 1 Coulomb from here, that battery will provide you 1.5 volts, 1.5 joules, because it has 1.5 volts. So as long as it has energy, as long as it still has, can do the trick. So when this runs out of juice, what you do, you go to the store and buy another one and basically have to pay for it. What it does for you is every time 1 Coulomb passes from one end to the other, it's going to provide you 1.5 joules of energy, okay? This one, on the other hand, does 9 joules for every electron that moves around it. This has more juice in it, has more energy in it. This is a 9-volt battery. Your car battery is 12-volt battery. So that means that for every Coulomb that the car basically drains off of it, it's going to give you 12 joules, okay? Your household, for example, in here has 120 volts. That is 120 volts per Coulomb That's 120 joules per coulomb. That means for every coulomb, you're going to get 120 joules from it. So that is the relationship between the voltage and the, and it's similar in a sense to the force in here and the electric field. The relationship between the force and the electric field is similar to the relationship between the energy and the electrical potential. Okay, they are actually similar in a sense because both of them involve Q in them. So this is the expression I was writing mathematically. It's the same thing. The electrical potential energy, which is in joules, is equal to the amount of charge in coulomb times the electrical potential. Okay, so this is the expression. 1 joule is equal to 1 volt times 1 coulomb, or 1 volt is equal to 1 joule divided by 1 coulomb. And that is the expression that I have in here. So again, the fact that you have tremendous amount of voltage, and I remember I mentioned that for that girl in here, and that is exactly what you guys experience if you happen to do this live. If we do a demo in here, you'll have tremendous amount of voltage, but remember, that depends on how much charge actually is moving in there. That's what dictates the fact that this person will actually burn or not. Okay, so if it's still a small amount of charge, it's fine. One way to store energy is through a device called the capacitor. Let me see if I can grab one of my kits in here to show you how the capacitor would look like. Hold on. Where is my kits in here? Transistor, diode, more diodes. Man, do I have any capacitors in here? Sorry, I don't have any. Okay, here is some of the diode, the transistors I was showing you earlier. This is the diode. This is part of the semiconductors. I have some resistors in here, and I think these are actually capacitors. Okay, I don't have my glasses to read them, but these are actually capacitors, and now I have the other bunch of resistors. Okay, so these are some of the electronic kits that I have in here, where I have a bunch of them, and again they store energy, they store charges. Okay, that's what the capacitors do. Okay, they store charges for you. Okay, so we had only a couple of questions today. And this is the Venn diagram, basically diagram for it. So we have only a couple of questions today, and I will see you guys later on for chapter. Kyle, you forgot them already? Can anybody remind me of what the two questions were? The second question has to do with the, okay, let me see. Okay. The second question has to do with the conservation of charge, and the first question has to do with the atoms basically have similar, not the same number of charges, and the same number of positive charges and negative charges, okay? And they have the same value, the same numerical value for the electric charge for that of the electron and the proton. The charge, by the way, is 1.6 times 10 to the negative 19. That is what is the charge basically of a proton. So 1.6 times 10 to the power negative 19. Both of them have the same value. To be picky, it's actually 1.602. Okay. So this is the charge, Coulomb, of course. Okay, this is the charge basically that is inside each and every one of them, and it's identical, regardless of where the electron or where the proton were made, whether they were made in Switzerland in the nuclear accelerator there, or they were made in Chicago in one of the two laboratories there in the nuclear accelerators, or they were made actually on the other side of the universe in a supernova. It's the same things. Okay. They are the same charge, and this is one of the peculiarities of this thing. Okay, I'll see you guys later on in the day for the Physics 11. For the others who are not sitting in Physics 11, I guess I will see you next week on Tuesday. Okay. And unless you guys has any other questions. So did you get the 2 questions, Kyle and everybody else? Yes, Sharon. We're going to talk about the conservation of charge and the fact that it's one of the main laws in nature. Okay. And let me know what you think about my musical number, whether or not I pass as a musician or not. See you guys next week for those in Physics 10. Bye. I'm going to stop the recording now.